aromatic character, chapter number 2. The introduction. The earliest use of the term aromatic was in the article by August William Hoffman in the year 1855. So there was a scientist named August William Hoffman. He was the first one to introduce the term. So he was the first one who introduced the term in an article. Hoffman used the term for a class of benzene compounds. So he did what? He used this term for nothing but a class of benzene compounds. So compounds of benzene are called as aromatic compounds, and he said that these compounds have aroma, or you can say odor. So these compounds, they have a special type of aroma or odor which is different from the pure saturated hydrocarbons. So he said that these compounds, they are benzene and its derivatives. They have a special type of aroma or odor, and their properties do not match. So they are different from the hydrocarbons, pure saturated hydrocarbons. So why do they smell so strong? So we say that aromatic compounds, they have a strong smell. Why they have a strong smell? They have a strong smell because of the presence of toluene. So they have a strong smell because of the presence of toluene in them. So the aromatic compounds, they have a strong smell because they have a presence of toluene. Also, there are certain types of mothballs which are available in the market. These also have a strong smell, but these have a strong smell because of naphthalene. They have a strong smell because of naphthalene. So what do we understand by the introduction? That the earliest use of the term was in an article by August William Hoffman in the year 1855. And he said that benzene and its derivatives are nothing but aromatic. Benzene and the derivatives of the benzene are nothing but aromatic. So he said that benzene and its derivatives are aromatic, and they have a special type of aroma, or they have a special type of odor. And this odor is different from the pure saturated hydrocarbons. So the aromatic characters, they have a strong smell because they are having a presence of an aromatic compound called toluene. So mothballs, they have a strong smell because of naphthalene present in them. So basically, the compounds which have a strong smell inside them will contain some or the other aromatic compound for imparting the smell. So what is actually aromaticity? Aromaticity as a chemical property bears no general relationship with olfactory properties of such compounds, that is how they smell. That is, there are some compounds that are chemically aromatic but they do not have distinct smell. So previously it was thought that aromatic compounds have a strong odor. So previously it was thought that all the aromatic compounds have a strong odor, but then it was realized that all of them don't have. So it was concluded that aromatic compounds are not the ones which smell. So it was concluded that it is not necessary that for a compound to be aromatic, it must have smell. That was the conclusion given, that it is not necessary for a compound to smell if it is aromatic. Because first all the compounds discovered contained some of the other smell. That's why they suggested a name of aromatic compounds. But because then it was concluded, it was realized that they had done a mistake. There were compounds in nature which were aromatic. So there were certain compounds which were what? Which were aromatic, but they did not have any smell as such. Any distinct smell was not present, did not have a distinct smell. But still they were aromatic. So they corrected themselves that it is not necessary that the aromatic characters will have olfactory connections, will always smell nice. So what are aromatic compounds then if they are not connected with smell? So they thought that if they are not connected with the smell part, then how do you distinguish that it is aromatic? How to distinguish whether it is aromatic or not? So aromaticity, it is a property of cyclic planar structures with rings of resonance bonds that gives increased stability compared to other geometric or connective arrangement with the same set of atoms. Now let us break this and understand. It is a property of cyclic planar structures. When I say that the structure is cyclic and planar, so let's take the example of benzene. Okay, so this benzene molecule is a planar molecule. It is a cyclic molecule. If you see that this is going like this, so we say that this molecule is cyclic. So it is basically cyclic. It is a planar structure with ring of resonant bonds. So this bond over here can shift and come over here. This bond can come over here. This bond can come over here. So this is forming a ring of resonating bonds and gives increased stability. So this can be given as a canonical structure like this. So it is said that the canonical forms are stable forms. So it is said that it gives increased stability compared to the other geometric or connective arrangements with the same set of atoms. So this aromatic compounds, they are cyclic, they are planar, and because of the ring of resonance, they give more stability than the saturated hydrocarbons or the same set of atoms. According to James Dever, aromatic system is a cyclic compound with a large resonance energy where all the angular atoms take part to form a single conjugate system. So if you say this, that is the benzene system, is a conjugate system. The system is a conjugate system. So why is it a conjugate system? Because all the atoms are contributing to that particular cyclic compound only. Okay. Next, Huckel's ruler. For a cyclic system to be aromatic, it must follow the Huckel's rule. Then what is the Huckel's rule? 4n plus 2 pi electrons. So it must have 4n plus 2 pi electrons. So if there are 0 electrons, so if n equal to 0, then 4 into 0 plus 2 equal to 2. If n equal to 1, then 4 plus 2 equal to 6 pi. If n equal to 2, then 4 2s are 8. 8 plus 2, 10 pi. If n equal to 3, then 4 into 3 plus 2, 12 into 2, 14. If n is equal to 4, then 4 into 4 plus 2, that is 16 plus 2, that is 18. And if n is equal to 5, then it is 22. So 20 plus 2, that is 22. So the value of n, so we understand that molecules which have 2 pi electrons, so where the molecules which have 2 pi electrons, have 6 pi electrons, have 10 pi electrons, 14 pi electrons, 18 pi electrons, 22 pi electrons, they are said to satisfy the 4n plus 2 rule, and therefore they are aromatic. So we say that for a molecule to be aromatic, for a compound to be aromatic, so what are the criteria which the compound should follow? A compound is said to be aromatic if it fulfills the following criteria. The molecule should be cyclic with a conjugated pi bonds. So cyclic it should be, therefore it must be something like this, cyclic compound. So the compound should be cyclic. Each atom in the ring must have an unhybridized p orbital. So one orbital should be unhybridized. The unhybridized p orbital must overlap to form continuous rings or parallel orbitals. The structure must be planar or nearly planar for effective overlapping. So this structure should have an unhybridized p orbital. This structure should be planar. So if it has an unhybridized orbital, p orbital, then it is planar. So that if it is planar, that means it has an unhybridized p orbital. So, and the last point is it should obey Huckel's rule. So what are the things? First is it should be cyclic. Then second is it should be planar. If it is planar, then it has a unhybridized p orbital. So we should find whether it is cyclic, whether it is planar, and whether it is following the Huckel's rule of 4n plus 2 pi electrons. If any of these conditions are violated, no aromaticity is possible. Now let us see what are the examples of aromatic compounds. So examples of aromatic compounds. So the first example is of ethylene. Ethylene obeys the Huckel's rule. Why does it obey? Because it is H2CH2. It contains, see, one pi bond is present, one sigma bond is present. So 1 and 2. So it contains 2 pi electrons. But is it conjugated system? Is it a cyclic conjugated system? It is not a cyclic structure. It is what? It is a planar. It is what? It is planar structure. It is not a cyclic structure. It obeys the Huckel's rule. It is a planar structure, but it is not a cyclic structure. Ring form nahi kar raha. That means it is non-aromatic. That means it is non-aromatic. So it has 2 pi electrons present, but because it was not cyclic, it was not following one condition, so we said it does not have aromatic character. For aromatic character, remember it should be cyclic, it should be planar, and it should follow the Huckel's rule of 4n plus 2 pi electrons. If any of these rules is violated, so any rule violated, okay, any rule violated, we say that compound is non-aromatic. We say compound is non-aromatic or anti-aromatic. So we say it is either non-aromatic or either it is anti-aromatic. Next is example cyclopentadiene. So how is cyclopentadiene? Wait. Like this, like this, like this, like this, and wait, and like this. 1, 2. So cyclopentadiene, is it conjugated? Answer is no. It has no delocalization of electrons. Because here the cycle is formed, then here there is no bond to carry forward this cycle. Again here it is formed, but here there is no electron is present to carry forward this cyclic motion. Therefore we say it is not cyclic, because it has no delocalized electron. Correct? So we say that cyclopentadiene is non-aromatic. Okay, next. If I take this cyclopentadiene, okay, if I take the same structure of cyclopentadiene, and if this, you notice this is what? This is carbon C, 1, 2 and H2, so 3, 4. That means it is sp3 hybridized. Okay, wait. Okay, wait. C, H2 and 1, 2. So 1, 2, 3, 4. So it has 4 sigma bonds. And we know when a compound has 4 sigma bonds, it is sp3 hybridized. So this compound is sp3 hybridized. Now from this sp3, so this is sp3 hybridized. So from this sp3 I am removing 1 electron. Let us say I do minus 1 electron. How will my structure look? So let's see how the structure looks now. See, like this, this and this will remain. Over here I am removing 1 electron, so this will become CH, okay, and with a minus sign. So I am removing the 1 pair of electrons and I am getting here a minus sign. Now is this structure aromatic? Let's check. So is this structure aromatic? Question mark. So let's check. So first we have to check for cyclic, whether this structure is cyclic. So this goes like this. Then these electrons will move like this and this will move like this. So yes, it is cyclic. Is it planar? Yes, it is a planar structure because all the bonds are in a single plane. And the third is whether it is following the Huckel's rule. So how to check whether it is following? 1, 2. So 2, 3, 4. 3, 4. And these are also 2. So 5, 6. So it has 6 pi electrons. When it has 6 pi electrons, we say it is obeying the Huckel's rule. So because it is 2 pi, then it was 6 pi, then you saw over here 10 pi, 14 pi, 18 pi, 22 pi, all these pi's it will obey. So it has 6 pi electron, therefore it obeys the Huckel's rule. Now if you don't remember this order of 2, 6, 10, 14, 18 and 22, no worries. 4n plus 2 pi electrons equal to 6 pi electrons. So you get 4n plus 2 equal to 6, because pi electron gets cancelled. So 4n equal to 6 minus 2. So 4n equal to 6, 1, 2, that is 4. So n equal to 1. If my n is a whole number, if my n is a whole number, then it will always be following the Huckel's ruler. So this should not come decimal or fraction. N should be always a whole number. So even if we don't remember this order of 2, 10, 14, 18 and 22, so on and so forth, no problem. We will solve it like this. So this is the Huckel's rule. And what is the name of this compound? This was cyclopentadiene. This will be because one of the electrons is removed. It becomes cyclopentadiene anion. Okay. Example number 2. Example number 2 is cycloheptatriene. Let's see cycloheptatriene. It is like this. Okay, so first we check for cyclic. So is this compound cyclic? This is there, this is there. This will go to this planar. But this plane is empty. This plane is empty. Therefore, we say that this compound is not cyclic. I will show it one more time. See. How do you check whether a compound is cyclic or no? This electron will go over here. The electron from this will go over here. The electron from this will go over here. But there is no electron over here to go over this planar. Therefore, this plane is empty. Therefore, it is not cyclic. So, because it is not cyclic, we reject this compound. We say that you are not aromatic. You are what? You are non-aromatic. You are not aromatic. You are non-aromatic. Okay. But now, what will I do? I will remove one electron. Okay. Rather than removing one electron, what will I do? I will take out. So I will make this sp3. This is sp3, correct? So I will be making this sp2. If I make this sp2, what will happen? I will get a structure like this. Correct? Here and here it will remain same here. But now because this is sp2, this is giving me a plus sign over here. Now is it cyclic? First we will check for cyclic. Is it cyclic? Let's see. This electron will go on this plane. This electron goes on this plane. This electron goes on this plane, and this positive plane, positive electron from the positive, there is an electron which is released, so that's why there is a positive sign which has come up, because plus is always losing the electrons, and when we write minus, when it is gain of electrons, so the electron which is lost will be delocalized and it will fill the space of this plane. So the plane was empty over here, now it got filled because of this plus sign. So cyclic is being followed. Even this molecule is planar. So two conditions are satisfied. Let's see the third condition. 1 electron, 2 electron. So number of pi electrons 1, 2, 3, 4, 5, 6. We say 6 pi electrons. And we know that 6 pi electrons means it follows the Huckel's rule. Even if we don't remember that 2, 6, 10, 14, 18, 22, we can still find out. How do we do it? 4n plus 2 pi electrons equal to 6 pi electrons. So pi electrons I cancel. 4n plus 2 equal to 6. 4n equal to 6 minus 2. 4n equal to 4, n equal to 1, when n equal to 1. So when n is a whole number, we say that it is definitely following the Huckel rule. So cycloheptatrine was not following the Huckel rule, but when I made sp3 into sp2, I got cycloheptatrilene cation, and this cation was following the Huckel's rule. This cation was following the Huckel's rule. Let's see the next example. Third example is cyclooctatetraene. 1, 2, 3, 4, 5, 6, 7, 8. So 1 bond, 2 bond, 3 bond, 4 bond. Let's see whether this is cyclic or no. So let's see. 1, 2, 3, 4. The condition 1 is cyclic. Is it followed? Yes, it is followed. Condition number 2 is planar. Is it planar? No, it is not planar. All the bonds are not lying on the same plane. So we say that the compound is not planar. Let's check the third condition. Third condition is Huckel's rule. So how do you check the Huckel's rule? Simple. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 pi electrons. So again, if you don't remember that order, what we do? 4n plus 2 pi electrons equal to 8 pi electrons. Pi electrons cancel. 4n plus 2 equal to 8. 4n equal to 8 minus 2. 4n equal to 6. n equal to 6 by 4, that is 3 by 2, that is 1.5. This is coming as a decimal. I said that whenever n comes as decimal or it comes as fraction, what do we conclude? We conclude that the compound is non-aromatic. The compound is non-aromatic. So cyclooctatetraene is non-aromatic. Thus these were the few examples. Now there is something which is interesting to know. We know that benzene will always undergo substitution reaction. It always undergoes substitution reaction. However, under certain drastic conditions, if you give it too much of temperature, too much of pressure, drastic conditions are provided, it will undergo addition reaction. But why does benzene not undergo addition reaction is important to note over here. We have seen that which compounds undergo substitution and which compounds they undergo addition. Let us see that first. So we know that compounds which have a single bond, like for example, the simplest example is ethane. Ethane is C2H6. It has single bonds. It will always undergo substitution reaction. And which compound will undergo addition reaction? The compounds which have a double bond. Compounds which have a double bond. Like for example, you have ethene and you have ethine. So ethene is C2H4. So how do you write this? C2H4. And how do you represent ethine? C2H2. So C triple bond H. So these compounds which have double bond or they have a triple bond in them, they will undergo addition reaction. Now, what is the understanding? See, this is the benzene. Benzene also has alternate double and triple bonds. That means benzene also has double bond in it. But still, benzene will not prefer addition reaction. Though benzene has presence of double bonds, still it does not prefer addition reaction. It will only do addition reaction. It will only do addition reaction when you provide it with drastic conditions. Otherwise, it will always be doing substitution reaction. Now, when you provide this drastic condition, what happens? It undergoes addition reaction forcefully, zabardasti, forcefully it undergoes. But there are breakage of bonds. So, the bonds, they break. And benzene does not want to willingly break the bond. So, it does not want to do all this willingly. So, bonds break hota hai, but it does not want to break the bonds. Still, it has to break the bonds. So, it does not prefer addition reaction. Why does not it prefer addition reaction? Because in addition reaction, it has to break the bonds. This bond has to be broken for addition reaction. For substitution, there is no need to break the bonds because benzene does not like to break the bonds. Therefore, it will always prefer substitution over addition. It will always prefer substitution. In case of drastic condition, it is forced to break the bonds, but it will always resist the force. Because for benzene, what is important? For benzene, it is important to remain stable. And for remaining stable, it cannot afford to break the bonds. Still, it will break under drastic conditions. Very, very important. Only addition will happen under drastic conditions. So, because you see a double bond in benzene, don't think that it is going to undergo addition like ethene and ethane or like alkene and alkyne. It will only undergo substitution reaction. Why will it undergo substitution? Because it has to be a stable molecule. It cannot afford to break the bond. So it will always undergo substitution reaction. Thank you.